Have you ever noticed that adding salt to ice water lowers its freezing point, or that sugary water boils at a higher temperature? These are real-life examples of colligative properties, properties that depend not on the type of solute, but on how many solute particles are present. In this video, we'll learn what colligative properties are, how they work, and how they can help us determine the molar mass of an unknown substance, a key application in chemistry. The word colligative, what are colligative properties? MES from the Latin colligatus, meaning bound together. Colligative properties are properties of a solution that depend only on the number of solute particles relative to solvent particles, not on their chemical nature. These properties are directly affected by concentration of solute particles, moles of solute, not identity solution properties like molarity, or mole fraction. There are four main colligative properties: lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure. When a non-volatile solute is added to a pure solvent, the vapor pressure decreases. Why? Because fewer solvent molecules are at the surface to evaporate, they are blocked by solute particles. Mathematically, this is expressed as relative lowering of vapor pressure is equal to P is equal to N plus N. Relative lowering of vapor pressure equals P naught minus P divided by P naught equals N divided by N plus N, where P naught is the vapor pressure of the pure solvent, P is the vapor pressure of the solution, N is the number of moles of solute, N is the number of moles of solvent. This principle forms the basis of Reynolds' law. P solution is equal to X solvent times P solvent. Adding solute raises the boiling point of a solution. Boiling occurs when vapor pressure equals atmospheric pressure. When vapor pressure is reduced by a solute, more heat is needed to boil the liquid. The elevation is given by delta Tb equals Kb multiplied by m, where delta Tb is boiling point elevation, Kb is the ebullioscopic constant, m is the molality of the solution. Example: salt water boils at a higher temperature than pure water. Adding solute lowers the freezing point of a solution. Why? Solute disrupts the formation of the solid structure, so freezing requires a lower temperature. The equation is delta Tf equals Kf times m, where delta Tf is freezing point depression, Kf is the cryoscopic constant, m is the molality real-world use. Adding salt to roads in winter lowers water's freezing point. Osmotic pressure is the pressure required to stop solvent flow through a semi-permeable membrane from pure solvent into solution. It's given by pi equals C into R into T, where pi is osmotic pressure, C is molarity, R is universal gas constant, T is temperature in Kelvin. Important terms: isotonic solutions, equal osmotic pressure; hypertonic, lower osmotic pressure; hypertonic, higher osmotic pressure. Reverse osmosis is used in water purification by applying pressure greater than osmotic pressure. Pure water is forced out, leaving impurities behind. Look at the figure. This diagram illustrates the process of reverse osmosis, where a pressure greater than the osmotic pressure is applied to salt water through a piston. A semi-permeable membrane, SPM, separates the salt water from fresh water, allowing only water molecules to pass through. Instead of water naturally moving from fresh to salt water, as in normal osmosis, the applied pressure forces water to move in the opposite direction from the salt water into the fresh water side. This results in the collection of pure water on the left side, which is released through the outlet. This is the fundamental principle behind RO water purification systems, used in RO filters for drinking water. Colligative properties can help us find the molar mass of an unknown solute. By measuring the change in boiling point, freezing point, or osmotic pressure and using known formulas, we calculate molar mass, m, equals 1000 times K times W squared divided by change in T times W1, where W2 equals mass of solute, W1 equals mass of solvent, K equals molar constant, Kb or Kf delta, T equals elevation or depression in temperature. This method is especially useful for macromolecules or substances that don't decompose easily. To summarize, colligative properties depend on number of solute particles, not their nature. They include lowering of vapor pressure, boiling point elevation, freezing point depression, osmotic pressure. These concepts allow us to determine molar mass of unknown solutes. Applications range from lab chemistry to RO water purification systems,